um,
Are you honest?
Spooky indeed.
um, okay, well, I'd like to talk about spooky physics, and I said it was in Minkowsky geometry, but actually then as I got into, because I thought I was just going to talk about EPR, but then I realized actually this also applies to the horizon problem in cosmology. So I'm moving a little bit, or I'm moving beyond Minkowsky geometry, but it's but the basic principles can be explained in Minkowsky geometry. And furthermore, in looking into this spooky physics, I realized that it actually goes back historically even to Newton. So I have a quote here from Isaac Newton. "'Tis unconceivable that inanimate brute matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact." And especially this phrase here, that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action or force may be conveyed from one to another, is to me so great an absurdity that basically only a fool would believe it. So this was Newton in a letter to the theologian Richard Bentley at the end of the 17th century. So he's basically talking about his theory of gravity, but saying that it has these weird properties. And it was actually Sandrine's son, Theo, who pointed this quote out to me. So I thank him. I thought it was quite interesting at the time. That was a couple of years ago, and then I sort of realized the connection to this other stuff that I was thinking about since this class on quantum mechanics last summer. It fits in, this quote from Newton fits in nicely in different sort of ways, different levels. Of course, he's talking about spooky action at a distance, even if he's not using the word spooky. It was probably dangerous to use a word like spooky back then. But it shows that this goes back a long time. But I also find it interesting because Newton was worried about this, and yet it was for very good reasons that Einstein later resolved by developing first special relativity and then his general relativistic theory of gravity, which showed that signals propagate at finite speeds, not instantaneously. And so stepping back from this even further, we can note that it actually is possible for someone working within the limitations of their own theory to sort of see the problems and be right about what's wrong with it, which is not obvious to do. I've heard people argue, well, we don't know what's wrong with our current theories. But at least from our vantage point of over 300 years, we can give Newton credit for being bang on about being worried about this problem, and it's actually, by a bit of a coincidence, it's still the problem that I want to talk about, which is action at a distance. And so how does that fit into physics today? Well, probably the biggest problem in theoretical physics is trying to unify quantum mechanics and relativity. And I want to argue that there's a spooky communication going on in quantum mechanics, especially with quantum entanglement, and that's going to be the main part of the talk today. I mean, this is stuff that's well known, but I think it's not quite emphasized as a path to move forward in physics. And so in fact, that's what I want to try and do here is sketch how I think we can try and move forward. Admittedly in a very it's a very small step that I propose to take here, but hopefully I'll convince you it's a step in a good direction. So in outline then, my goals are to try and convince you that we're still haunted by spooky action at a distance, and to try and use this as a way to move forward in theoretical physics today. And the spooky physics I want to look at, as I said, especially the one in quantum mechanics coming from correlations, that goes under the name EPR today. This is definitely spooky stuff. And but I realize it goes beyond that. There's in cosmology, we have something called the horizon problem. And that's maybe a little bit spooky. And then I'll conclude with how we might move forward. The cosmic horizon problem is, as I say, is less spooky because we think we have solutions to this problem, but it's maybe useful for me to present it, even if really rapidly, because it gives some of the background on things like causally disconnected events, and it also shows that if we can make progress on this spooky action at a distance, it goes beyond just quantum correlations in EPR. It might touch other areas of physics, such as cosmology. So what's the cosmic horizon problem? Well, first I have to explain the CMB, the cosmic microwave background, and its properties, that it's essentially isotropic, and then explain why that's spooky. And I'm hoping I can go through this fairly quickly, because I think you're not physicists, but you've been exposed to this sort of thing, right? I think you've heard of the maybe I should be following the chat, so in case there's people screaming at me in the chat. Yeah, so if you have of course I have to find the chat now. Yeah, okay, so here's the chat, and I'll try and glance at that from time to time. So if there's something, of course you can just speak up, right? Cut me off if you're really bothered by something, but you can also type here in the chat, and I'll try and keep an eye on that. Yeah, so the CMB is the cosmic microwave background. It's microwaves that we measure today at about just below 3 degrees Kelvin. They come from all directions in space. They're relics from, the photons are relics from processes in the Big Bang. And they're extremely dense. There's over 400 of the photons per cubic centimeter. The key thing is that they provide, or they're the most useful piece of data cosmologists have. And they provide a snapshot of the temperature of the universe about 380,000 years after the Big Bang. They're a sort of temperature measurement, and so how does that work? Well, just a little bit before that, say 370,000 years before or after the Big Bang, they were the radiation at that time was tightly coupled to matter. The matter was essentially the ionized hydrogen and helium, and those dominated the ordinary matter of the universe. But then by about 380,000 years after the Big Bang, the temperature cooled to below a critical threshold of 3000 Kelvin, and then which allowed the photons to, we say, decouple from the matter. So they no longer interacted with the matter. And so they're no longer measuring the temperature. In fact, they just propagate freely through space and have been traveling for, close to 4 billion years before they're detected here on Earth. So we can look out in any direction, and we'll see these photons coming to us, and they're highly isotropic. And so I've plotted or I've pilfered this image of someone who's plotted the CMB over the whole sky, right? So it's a sphere. So you have this map projection problem, and the same map projection problem you have projecting the globe onto a map. And onto a world map. So this is supposed to represent a sphere, and the colors represent the temperature. But it looks like there's a lot of variation, and these little variations are tiny little details. There are a few parts per 100,000. The temperature is basically that 2.725 ... temperature. Is just tiny little variations, and that's what you're seeing here. So the take-home message for us today is that the temperature is the same wherever you look, to high precision, and that the temperature we're talking about is the surface of a sphere that was formed when the temperature measurement was taken was 380,000 years after the Big Bang. So why is this isotropy spooky? Well, because it's spooky because different parts of this sphere are causally disconnected. And I think that might be familiar to you, but I'll just maybe spell that out. Maybe I can ask Jean-Philippe. Jean-Philippe, does that need to be spelled out?
What exactly?
Causally disconnected.
Oh, well, I don't know.
I'll take that as a yes.
It means you need to go faster than the speed of light to go from one point to the other.
Yeah, to communicate between the different parts on the sphere. So the fact that they're the same temperature means that it's a funny coincidence that they're at the same temperature, right? Because they're causally disconnected. I have a diagram that can maybe so yeah, I think I'm going to skip some of the.
But Rob, can I ask you what makes you say that they are necessarily causally disconnected?
Yeah, they're because their past light cones don't overlap.
Why?
Okay. Well, here's my diagram here of the here's a space-time diagram. I've done it in Minkowsky space, but which doesn't exactly apply, but it allows me to present the idea very simply, and so I hope you'll allow me that simplification. So I have time on the vertical axis. So this is time from the Big Bang. And this is t equals 0 when the Big Bang happened. So the Big Bang is this red line. So the horizontal axis is a spatial axis. We could add 2 more space dimensions, but it would just sort of complicate the picture without giving us any benefit. So at about 380,000 years, we have a space-time event here. And I'm saying this space-time event is like a photon measuring measuring the temperature of the last particle it's going to interact with before it goes flying off into the future, and eventually to be received by some detector in New Jersey. so this this space-time event is the measurement of that temperature of that gas. And if we move over here in space, but at the same epoch here, we might have another event, B, which is another photon doing the similar thing. And its past light cone intersects this past light cone. So we can imagine some process that propagates forward here and affects this temperature here. And the same process could propagate forward here and affect this temperature here. And so we're not surprised that A and B are the same temperature because they're causally connected. Their past light cones overlap here. And by the way, I should have, what I forgot to say, which is maybe the most important thing, is that what caused the temperature to be whatever it is here at the point A when it was measured, or the event A? It could be a lot of things, a lot of physical processes, but they all have to take place in a space-time that falls within what we call the past light cone of this space-time event. And so the past light cone of this event here is just is outlined by the null geodesics extending backwards in time, which in this one-dimensional diagram just looks like a triangle, right? I have this line here and this line here. That would be a light ray leading to this event there. And I guess if we added one more spatial dimension, then the actual shape of this this surface would be instead of two sides of a triangle here, you do the rotation about the time axis, and that would define a cone with axis about the vertical time axis here. And if we added another spatial dimension, what we would have, it would be spheres starting at 0 radius here and increasing in radius as I move backwards in time to the Big Bang. But
maybe I can precise a little what I meant to say, but yeah, go on. I'll go back to my question afterwards.
Oh, okay. So I just want to point out that this space-time event here, C, is the measurement of another photon measuring a different part of this plasma at 380,000 years after the Big Bang. But its past light cone doesn't overlap the light cone of the past light cone of A. And so there's no sort of common event or process that can lead to the same temperature in A and C. So if they have the same temperature, then it's considered some sort of spooky coincidence.
And also there's something about the Big Bang that is assumed to be extremely uniform and regular. And so you would expect, however big it is, that the conditions are uniformly distributed on the Big Bang itself. And so in the past light cone of all these events on the last scattering surface, there is a similar set of conditions that naturally will entail similar temperature.
Okay, I guess I'm a little surprised that I'm having to defend the horizon problem. So this was a big problem in cosmology in the 1970s. Maybe in the interest of time, I can say the short answer to your charges is I'm not sure I'm going to be able to defend the horizon problem in the next few minutes without losing, or certainly not without losing the whole thread of my talk. So I hesitate to spend too much time on this. But I can say that at the time it was it was by no means assumed that we had a specific cosmology. If anything, they were leaning towards the closed Friedman-Robertson-Walker universe at that time. And so this applies to the closed case as well. And I mean, there's an obvious solution that you can say, the universe went back further than the Big Bang, and that this wasn't the start of the whole thing. It's always interesting to me what people question, but yeah, maybe in the interest of maintaining the thread of the talk, I'll just continue on. This problem was considered solved. Well, I should say a solution was proposed by Alan Guth to the horizon problem in the late 70s. Here's one of the early papers in 1981. He proposed this thing called inflation, cosmic inflation, which is a rapid expansion of the universe in the first minute fractions of a second after the singularity. A very large, the scale factor went up by 10 to the 26. This solved the problem because you could effectively get superluminal communication between different parts, just because the universe was expanding so quickly. The universe was expanding superluminally, and this does not violate relativity. But it's speculative, right? Because they don't know the mechanism for what's causing this rapid inflation. But people beavered away and developed the idea, and they found that this hypothesis, I guess, the inflation hypothesis, made predictions that could be tested, and were found to be true or consistent with the observations. And so it gained more and more acceptance. It's not universally accepted because there's a certain amount of skepticism because we don't know this, the mechanism behind it, and it just seemed a bit ad hoc to postulate this rapid expansion. Okay, so that's the cosmic horizon problem, and some of the notions of causally connected. Now I want to talk about the main thing, which is the Einstein-Podolosky-Rosen experiment, which is some spooky physics. So I'll give you a little history on this experiment, and then I want to show you the presentation that I showed in this MR2 class in the summer, based on an article by David Merman. There are many versions that you can present of this thing, including the Bell inequality version, but the message is the same. You have some kind of funny statistics that you can't explain in a sort of using classical reasoning and classical statistical analysis, but you can explain the data using quantum statistics, and it turns around this idea of an entangled state that I'll show you, and I'll show you an example of, and then I'll explain what's called the no signaling theorem, and then I want to discuss what I think the message from EPR is. I think it's that there's some kind of funny, spooky action at a distance, even if it's not one that you could exploit to send signals. Okay, so very briefly on the history of this, whole idea that is now called the EPR result or paradox or experiment, what started as a thought experiment by Albert Einstein and Podolosky and Rosen, published in 1935. It was described as a more practical experimental setup using a pair of entangled spin 1/2 particles by David Bohm. And I wanted to emphasize that because I feel like he doesn't sort of get credit for this somehow. People mention Bell and EPR and Alan Aspect and others, but nobody mentions Bohm. But it was actually Bohm who set up this, at least conceptually set up this experiment based on Einstein and others. John Bell's work on it was to show that if you analyzed the experiment classically, for example, using the notion of hidden variables, and did a classical statistical analysis, you can derive these inequalities that could be violated by quantum statistics. And then later, several people, including Alan Aspect, showed that they actually performed the experiment or a version of the experiment and showed that quantum statistics apply, violating the Bell inequalities. So showing that the world is in this sense quantum mechanical and not classical, and that yeah. Okay. So at this point, I'm going to switch to my other presentation, if I can find that. Oh, I think it doesn't work unless I have the thing expanded, right? Okay, share screen book. I actually wrote a 132-page book for this class. And this is chapter 7. So if anyone's interested in this book, I don't think I plan on publishing it or not anytime soon, but if you're interested in reading it, I'd be happy to share it with you. If you were in the class, I should have sent it to you. So maybe you have it already. Let me start with the experiment. So this is David Merman's version of the EPR thought experiment, or the David Bohm version of the EPR thought experiment. And I have a diagram here showing the experimental setup schematically. So you have a source here, which produces, I think you can still see me, right, in the video. So you have this source here, and it's producing a pair of particles that fly apart in opposite directions. And so this particle, say A, goes towards detector A, which is going to measure the spin of that particle A. And the detector can be oriented in different directions. So we measure spin along a spatial axis. So the axis of this spin detector A is going to be, the axis is going to lie in the XZ plane. But Alice, it's going to be Alice here controlling detector A, and Bob is going to control detector B, which measures particle B, which also measures spin in the XZ plane. But Alice and Bob can turn their detectors so that they measure the spin along different axes. So if Alice has her detector pointed straight up here, or in the vertical, say, she measures, or let's call that parameter, detector setting 1, then A for Alice's detector, then that's she's measuring along the z-axis. But she can turn it down here, so it's measuring the spin along this axis, 120 degrees from the other, from straight up, and she can also turn it to, say, another setting, which we'll call a = 2, which is oriented this way. Of course, there are many different versions of this. You can explain this whole thing and derive Bell inequalities if you just choose two different directions. It doesn't really, or there are many possibilities. But this is the one David Merman sets up, and I quite liked his approach, because he doesn't go into Bell inequalities, but he just kind of tells you, imagine we did this experiment, and the way we did it was Alice so the particle pair is emitted here, and just before the particle is about to be detected by Alice's detector, she turns her she rolls a dice or something, somehow randomly chooses the orientation of her detector, and then does a measurement. And Bob does something similar here. But see, the measurement, the choice of orientation of the detector and the measurement by that detector are events that are space-like separated from those events in Bob's lab are space-like separated from those in Alice's lab. That's important, because it means that there is no way that Bob could know about what Alice is doing. Even if they were like trying to cheat and send surreptitious signals to each other, they couldn't, because special relativity says that there's those measurements and the orientation of the choice of the orientation of the detector made just before the measurement, those are space-like separated between the two detectors. So there can be no signaling between them. And that's going to be interesting. Why, when we describe the properties of the data that they measure, so what does that look like? I'll show you here. So when we record the data, here's a brief summary of hopefully everything I've just said. Well, I forgot to say that was for one pair of particles, but then we repeat this many times so we can get lots of statistics on this. And the choice of detector orientation is random, but also uniformly random. So it's equally likely that she puts it in any one setting. Same for Bob. And so when we record the data of this experiment, we have to record Alice's choice of her detector setting, little a, Bob's choice of his detector setting, little b, and then the result of the measurement by Alice and the result of the measurement by Bob. Yeah, and so I forgot to mention, we're measuring spin here, and so spin, we're measuring spin along an axis, and the answer is either it's spin up or spin down. So in this experiment by David Merman, he says we're going to associate, Alice is going to associate spin up with the color green and spin down with red, and Bob does the inverse. Here's the properties of the data that they're going to obtain from this experiment. It's a hypothetical experiment, but in principle it could be done, and it's the sort of thing that Alan Aspect and colleagues managed to do. So maybe I'll start with data property 2 here. Data property 2 is implicit in what I was just saying about it's equally likely that that they choose any given detector setting, and the properties of the, well, here's the joint probability distribution of the what Alice will observe and Bob will observe. So she's so a quarter of the time she'll measure green and he'll measure green. So in quantum mechanical terms, that means she measured spin up and he measured spin down. And 25% of the time she measures red and he measures green. So they measured the same spin. So that's the summary of the joint probability distributions. But then there's another data property that is very curious. It's that when Alice and Bob chose the same detector settings, now this had to happen by some kind of coincidence, right? Because they're doing it randomly, and they're space-like separated events, so they couldn't share that information with each other. But by coincidence, I think a third of the time they're going to make the same choice of detector setting. And so when that happens, they must measure the same thing. So that'll mean or the same, they're going to get both green or both red, and so that's going to correspond to spin up and spin down. I'm immediately making the connection with the quantum mechanical version of the experiment. The way that David Merman sets it up is he just doesn't say anything about quantum mechanics, and then says, imagine you had an experiment in which you had this data, and with these two data properties, data property 1 and 2, and he asks you to try and imagine how that could possibly come about. And you're allowed to imagine, well, I have 8 different types of particles, and they have such and such a interaction with detectors, etc. You cannot reproduce this data. Unfortunately, I don't have I don't have time to go through it all, but I'll just leave it as a sort of challenge to you. The way he does in the paper is he asks you to try and come up with a mechanism using sort of classical thinking and reasoning, how this could work, and it's just impossible. If you may, I invite you to go try. If you can think of something that would work, that you'd have a very nice paper instantly. Of course, another way to present this is to show derive the Bell inequalities, and then which are based on classical statistics, and then you would show that a quantum using quantum correlations, you can violate these Bell inequalities. But Merman's approach is more, or I find one advantage of it is it forces you to try and think of a physical mechanism. When you realize that it's really frustrating, you can't think of how this could possibly work. To me, that really highlights the funny nature of this experiment. And so I just want to go back to, I guess, yeah, this diagram here, and say the really amazing thing is, so if Alice puts it's this data property 1, like if Alice is measuring along the z-axis and by chance Bob is measuring along the z-axis, she's going to measure well, and if she measures spin up, he's going to measure spin down. That has to happen that way. And it's just it's as if Bob's detector and particles somehow know what position Alice has her detector in. But that's exactly the thing we try to avoid by making these space-like separated, decisions or events that correspond to the decision of the orientation of the detector and the measurement. Okay.
Sorry, Rob, can I just ask a quick question? So this is all in the framework of special relativity, in which you have a global notion of z-axis. Now, space-time is curved, and I suppose one has tried to organize an experiment that would be an analog of the EPR situation on a curved situation, but that could be done in orbit or something like that. But how do you make sense of this sort of thing in a curved situation? Because you would, I mean, one obvious answer would be parallel transport, but then along what? Because there's not supposed to be any propagation of information, and parallel transport along two different geodesics going from one point to another, which is possible with gravitational lensing, would give you two different directions.
Yeah.
Of course, at this sort of scale, I'm positive that this has not been done, but but it's a fair question, I think.
Yeah, not experimentally, but yeah, I remember looking into this a couple years ago, and I think people have recently thought about this, and I've seen some papers on it. But yeah, it's interesting. Yeah, in short, the notion of the z-axis is only pointing in the direction of the z-axis there, only makes sense in flat spacetime. And
yeah, sure.
hello.
He's not attending the seminar.
Yeah, that's a nice question. Let me try and go back to the other thing. Oh darn, that's not possible. Oh darn. Hang on 1 minute, please. I have to open the. Oh dear. There it is. Oh, okay. I have to open that window and then share screen, seminar. Okay, so so as I say, you can reproduce these these two data properties, not with any hidden variables or classical thinking, but by using quantum particles that are spin 1/2 particles, but they need to be in this quantum singlet state, which I've written here for you, and I'm here's my quantum singlet state. So I have two particles, A and B, and we're focusing just on their spin state. So states are represented with these vectors in a Hilbert space, but we just have a two-dimensional Hilbert space because we just have the two states. They're either spin up or spin down, and but we need a ket vector, state vector, for each particle. A and B, and so I'm using plus for spin up and negative for spin down, and it's the because we have the two particles, we have the tensor product of these two ket vectors. But the so just looking at this part of this ket vector here, we would say that, well, particle A is spin up and particle B is spin down. But we don't just have that. In quantum mechanics, we can have these funny superpositions. So I have that minus this other tensor product of two possible vectors, which is particle A is spin down and particle B is spin up. And so this is this singlet state, and the one over root 2 here is a normalization factor such that this skew symmetric inner product gives unity. And I don't think we normally write vectors in this way. In quantum mechanical books, you'll see just this notation here. So they've combined this into one vector, and you're just supposed to remember that the symbol on the left here means the particle, one particle, and the symbol on the right means the other particle. And yeah, so that's the notation. And with this state, you can reproduce these statistics. And I guess maybe I should say also that when you take a measurement, you collapse the wave function. So what happens is the one of these two gets selected, and yeah. Now an immediate reaction to this experiment is to suggest that there seems to be an obvious sort of violation of special relativity, because it's like as I say, it's almost as if particle B at Bob's detector knows about the setting of Alice's detector, but there's something more. There's something subtle going on here, where you can show that it's actually impossible for Alice to send a signal to Bob, and vice versa. Bob cannot. By the symmetries, Bob can't send a signal to Alice either. So let me explain that here, because it's kind of critical. So let's say Alice wants to send a signal. Well, she has to change something that's under her control, and that has to be somehow observable to Bob. So what's under her control is her detector settings. And so she can change this little a to a equals 1, 2, or 3, just corresponding to those 3 possible orientations of her detector. What does Bob observe? Bob only observes the output of his measurement, so the value of this capital B, so either the green flash or the red flash, or spin up or spin down, along whatever axis he chooses for his so whatever little b he chooses here. So, but unfortunately for Alice, if she wants to send him a signal, is that oh, sorry, I forgot to mention that. So Bob only observes B. So it's the marginal probability of this joint probability distribution, right? So I have to sum over A to get the observable that Bob sees. So I sum over A for all these probabilities. Those are the probabilities that Bob will observe when Alice has her detector in position A, or in position B, sorry, A equals 1 or A equals 2 or A equals 3. But no matter what she chooses for her orientation, which of the three, they all lead to identical probabilities for the marginal probability that Bob can observe. And that's true for all values of little b that Bob can choose. And by symmetry, this works in the other way. And so I wrote that out for you if you like. But so Alice observes her marginal probability. So, excuse me, sum over b. And no matter what Bob does, whatever setting Bob uses, b equals 1, 2, or 3, or little b, Alice's marginal probability is the same. And that's true for all her detector settings. So that's called the no signaling theorem, or that's an example of a more general no signaling theorem. We can't use this to send signals fast or information faster than the speed of light. But nonetheless, there's something funny going on, right? And because we can't reproduce these results with classical statistics. So now really quickly, I guess I wanted to just summarize this situation. I think I'll skip over this. Most physicists are not really too concerned about this. My reaction to it is that I think we should be interested in it. I think that it's a starting point to new physics, because there's some kind of superluminal signaling going on, even if it's not of some practical form that can be exploited for communication. So even given the constraints of the no signaling theorem, there's still something going on here, and that's very non-classical. And I think we should try and make sense of this. And I have a quote from David Merman, his sort of conclusion on it, which is mostly sympathetic with what I just said. He basically, I'll just draw your attention to, he says the EPR experiment is as close to magic as any physical phenomenon I know of. But he doesn't, he's more agnostic about whether we are going to learn any new physics about this, more agnostic than me. I think this is really the starting point, because he admits that there's some kind of action at a distance, even if you can't use it to send signals. So even if we're constrained by the no signaling theorem. So very briefly, I wanted to suggest maybe how we could move forward, and these are sort of my own tentative speculations, really. I guess, yeah, if you'll give me just 2 minutes here, I'll tell you what I've been thinking about. How can we make sense of this? How can we have some kind of signaling going on without violating the sort of Lorentzian manifold structure of space-time? Because I think we don't want to give that up, and we want to admit that the world is quantum mechanical, but GR, general relativity, and quantum mechanics are just approximations. I think physicists would agree that at very small length scales, basically the Planck scales, so small length and time scales or small energy scales. Actually, it's not so small in the energy, but in small space and time scales, we don't know the structure of space-time. That's just an unknown. And finally, this is sort of very hand-wavy, loose thinking here, but where does the arrow of time come from? This is something I looked into recently, and it's basically from the second law of thermodynamics. Most of the laws, or all of the laws of physics, are time reversal invariant. If you change the parity and the charge, but the exception is the second law of thermodynamics, but the second law of thermodynamics is a statistical law, which implies that you need some sort of averaging there to get the entropy of the closed system to increase. So here's my postulate. This is my postulate, is that at some sort, so we have an arrow of time. So causation moves forward in time. But that is a resolution dependent phenomenon, perhaps. Perhaps if we looked at the arrow of time in a very minute scale, maybe at the Planck scale, it wouldn't make sense to look any smaller, but at some small scale, perhaps as small as the Planck scale, then causation can flow in two directions. I admittedly, that even sounds wacky to me at first, but then let's go with it for at least to entertain the possibility. And here's an interesting thing about Minkowski space, is that basically, if I take any two space-like separated events in Minkowski geometry, again, it's just in one space dimension and one time dimension here. Time's always on the vertical in relativity. So this is one plus one Minkowski geometry. If I take two space-like separated events, A and B, along their past light cones are going to intersect at some point C, as long as we're not near the I guess the Big Bang. Then they're going to intersect here, and then the interesting thing is that there's zero proper time separation between A and C. So if you're so here's the proper time separation between events A and C in that diagram is just there's a finite coordinate time separation and a space time separation, but the proper time separation between them is zero. So there's essentially zero time between A and C, or proper time between A and C. So maybe it's not a stretch that you can have an sort of backwards influence of A on C. But then once you've had A influencing C, then it's easy to see how C, the event C can then influence B. There's no controversy there. It can just send a photon. And so that's my speculative, controversial, or presumably controversial hypothesis, that A could influence C, and then once that's the case, then you can relay this effect onto B. So in other words, we're finding a way of I'm trying to obey Minkowski geometry here, but send signals from A to B in this way. That's my hypothesis. So we can stop there, and hopefully you're not too shocked by that. So I'll entertain your questions.
Speechless.